Hello everyone, and welcome back to a new episode of Advent of Code 2016. We are doing day 14 today, or, well, I should say you guys are doing day 14. This is another one of those episodes where I did the problem off camera, but would like to go over it with you guys, since, as always, they're interesting. There's a number of useful points to go over, and it can just be fun to see how someone else solved it if you are following along at home, or just see what the heck this is all about if you're not following along at home. So day 14, one-time pad. In order to communicate securely with Santa while you're on this mission, you've been using a one-time pad that you generate using a pre-agreed algorithm, but you've run out of keys and you need to make some more. To generate keys, you first get a stream of random data by taking the MD5 of a pre-arranged salt, which is your puzzle input, and increasing integer index. So this is very much like one of those previous days, I forget which one, like 4, 3, something like that, where we had to search for MD5s that started with 5 zeros. Okay, we're doing something similar here. We have a start value and we're adding numbers to the end of it and we're taking MD5s of those things. Fine. However, not all of these MD5s are keys, and you need 64 new keys for your one-time pad. A hash is a key only if it contains 3 of the same character in a row, such as 777. Only consider the first such triplet in a hash. So if you generate a hash that's 111, 222, 333, 444, only the 1 counts as a triple. Additionally, one of the next 1,000 hashes in the stream contains that same character 5 times in a row, like 5 sevens. Just because you're thinking about a stream in the future, or a hash in the future, and using it as like a triple, doesn't mean it... Basically, you have to look ahead to what future hashes are in order to decide if this hash is valid, but those future hashes can still be valid. You don't skip over them because you're using them to see if the current hash is valid. And then they have some example and blah, blah, blah. So, what do we do here? Well, the first thing is, so what I did as I was solving this is I took git snapshots, commits, I suppose, a fair enough thing to say. I took snapshots by creating a git commit at various points during the solving of this this program so that I could, I didn't really do it in mind of saying, oh, let's stop here and look, and then show you guys the next version. But that is what I'm going to do. So we're going to look at each of the commits that I made separately. There's not actually that much difference between them, really. It's more, I think, instructive to discuss for a while. In fact, let's put away the code and go look. We'll just look at the screen and we'll talk a little. How's that? About some approaches that I tried or thought about that weren't going to work. I didn't get as far as actually implementing something all the way before realizing it wouldn't work, but I definitely got at least a little ways in a few times. So the most obvious thing you could do is you could generate a hash, check and see if it has a triple, and if so, look through the next 1,000 numbers and generate all their hashes looking for quintuples. Okay, so that's doing 1,000 times as much work as you need to, if you assume that the most expensive thing happening is MD5s, basically, right? At each step, you're generating 1,001 hashes instead of just 1. So that's an approach that is plausible. And in fact, for part 1 anyway, that would be good enough. You would finish the whole thing in, I don't know, a minute, less than a minute, I'm not sure, something in that neighborhood. So you could do that, but it does not seem elegant at all, and I never considered doing that. Even if it is going to work, it's dreadful, right? So let's not do that. What I thought about next was a way that you could not generate any unnecessary MD5s. My plan was basically to, as we're scanning over the list of inputs, well, it's not really a list, right? It's an iterator of all the possible things we could hash, whatever. But imagine conceptually we have a series of MD5 values coming in, and we just need to look at them. The fact that we generate them from a salt plus an int is not interesting. They're just MD5s, right? Each time we look at a hash, if it has a triple, we sort of put it into a queue, and don't emit it right away. Then, when we if we see one with a quintuple, we look through the queue of pending things to output, and for each one whose triple that we saved in the queue matches the quintuple that we just found, we output it. That way, we're only computing a hash once. So we have to save in the queue like what index the thing was at, so that we know if the quintuple that we've found is recent enough. And if not, then we remove the thing from the queue. Well, we remove the triple we found if it matched. Anyway. So I think you guys see that sort of the ideas. We have a queue of matches, and every time we get a quintuple, we scan that queue and output everything from that has the right triple for the quintuple that we found. And I got I don't know, a dozen lines in or so using that approach. Let's look at the code now, even though it's not really relevant. I forgot to reload. This is an older version. Good. We were looking for a moment there at my my actual final version, but okay. Here's my first git commit, and you can see that I was debugging something. Like, I was getting an answer that it said was too high, and I tried it with the sample, and it's like, oh, that's wrong too. Great. Couldn't figure out why, so I committed it. Anyway, I got some ways in with this queue approach, and I realized that, well, actually, before I even started implementing the single queue approach, I realized, wait a minute. It's really hard to scan through a whole queue, remove elements from the middle if they match, and right? So I realized, wait a minute, we should have 16 queues, one for each character that could appear in a hash. And then when we find a quintuple, we scan just through the right queue to find numbers that match. Great. But a problem that approach and the approach that I described a minute ago share is that while you output all of the right matches, you don't output them in the right order. Because maybe I find at index 0, I find a hash with 3 A's in it. And then at index 10, I find a hash with 3 5's in it. And then at index 30, I find a hash with 5 5's in it, and so I release the second one. And then, at index 100, I find a hash with 5 A's in it, and I release the first one. That's great. They both are supposed to be released, but I got them in the wrong order, which is going to really mess up being able to solve the problem, which asks which hash is the 64th one that you find. So I never actually finished that approach. It's possible that I would have gotten lucky, and they would have happened to come out in close enough to the right order, but it was clearly wrong, so I didn't do it. Okay, fine. So what I came to then was gosh, it's really hard to have an approach where you only hash, where you don't do any extra hashing. And so what I decided to do instead is what you see on the screen. I have a look-ahead map, which is just a map from character to int of... So the idea is we're going to pre-compute 1,000 hashes from 0 to 999. And every time I hash the input number n, I'll also update my look-ahead hash for n plus 1,000. And then whenever I find a triple, I'll just look in the look-ahead hash and say, hey, are there any things that match this coming up in the next 1,000 items? And then the answer will either be yes, I should emit it, or no, I shouldn't. Right? So, that that is the approach that I tried. And so basically what we do is we just have a function key that like returns the MD5 of our puzzle input plus this the stir of the n that we want as hex. And the main algorithm here is OTP keys, which has two parts. First, we warm up the look-ahead cache. We define a function update look-ahead that takes an n, and basically it finds all the matches in the string of the same of a single character occurring 5 times in a row, scanning, of course, the key for the nth number. For each one, it updates the look-ahead to be that number. Great. And then we say, hey, please update the look-ahead for all the numbers from 0 to 999. And now that we're done warming up, we start just looping forever through all the integers starting at 0. First, we update the look-ahead for I plus 1,000. And then we find the first triple in our key, if there is one. Oh, right. This is... Don't monkey with the past. This is not the latest version. There are future commits upcoming. Okay. So anyway, I say if we have a triple and the look-ahead for that triple's number is greater than or equal to I, then yield I. Great. Seems reasonable. And I just say, hey, please produce a sequence. So what we get is, in effect, a sequence of keys. And then later in main, we'll count how many keys, or we'll grab the first 64 and look at the 64th one or whatever. But actually what I do is I don't even have Python do the counting to 64. I just have it output them forever and then use shell tools like head and tail to pull out the 64th one. It seemed nice to have this Python thing output all of them so that I could like look at the output and say why is it wrong? Okay, so if you guys want, pause the video, maybe look at this, see if you can see what's wrong with this version. Because I said something is wrong, we get a number that's too low. Yeah, too low. So, like I said, if you're excited to figure out what's wrong, go ahead, pause the video, take a look. Okay, great, welcome back. So we're just going to get rebase, continue. What? What does this mean? Okay, I see. The rebase I was doing deleted the directory I was in temporarily. That makes sense. All right, whatever. Get rebase, continue. And we'll now go look at the next commit I made, which is very small. If you were watching carefully, you might have seen this is what changed. It was greater than or equal to, and now it's greater than. And I also put this key back to be the actual puzzle key. So this was the problem, was that this was something I told myself to remember not to do, but I still did it, is any quintuples in the current hash should not count for qualifying triples in the current hash. But that means that if the look-ahead... This actually seems like I'm still not... I didn't quite have the correct fix, did I? It worked, but it was wrong. What I should have done is move this part to here. Right? And I know, we're not monkeying with the past, I'll put it back. But, actually I could leave it there, I guess. The problem is that when I call this update look-ahead thing, if the current thing has a quintuple, in the old version where I had greater than or equal to, then I was accidentally allowing some keys that I should not have allowed, because they have quintuples and triples in them. So, fine, replace it with a less than, and now the problem that I just noticed is, what if there's something with a quintuple, but there's also something in the future with a matching quintuple? I should allow that key, but I can't because I've erased that look-ahead entry, right, and replaced it with one that doesn't count. So what I definitely should have done is this is a better approach. And if I do that, then I still need this greater than, but I should have this come after I decide whether to include the current key. Okay, well, that's exciting. Anyway, this gets the right answer for part 1. So let's go look at the next version. Oh, actually, before we do that, let's go look at part 2. Of course, in order to make this process even more secure, you've also implemented key stretching. Key stretching forces attackers to spend more time generating hashes. Unfortunately, it forces everyone else to spend more time too. To implement key stretching, whenever you generate a hash, before you use it, you must find the MD5 of that hash, and then the MD5 of that hash, and so on, a total of 2016 more times. For example, to find the stretched hash for index 0, you find the MD5 hash of ABC0, and then hash it and hash it and hash it and hash it 2016 times. And then the whole rest of the thing is the same. So what this has had the effect of is to make it much more expensive to compute hashes unnecessarily, right? The first version I described, the most super naive thing you could do of not storing anything, and every time you think you have a candidate answer, look ahead and compute the hashes of 1,000 things. Well, basically, he's made the problem 2,000 times as hard, and at that point, it becomes pretty expensive to make it 1,000 times harder yourself voluntarily. So, fine. Before I actually started solving part 2, what I did was I had, rather than printing all the outputs, I use iSlice to grab exactly the 64th one, and I print that, so that I can output 2 numbers. It was going to be kind of hard to use head and tail to, like... Basically, I was going to have to slice it so I could compute only 64 hashes. We can't just yield numbers forever from part 1, because we have to get to part 2 eventually. So I did that. Fine. What's next? Make the hash function a parameter. So what I did is not yet start on part 2, but instead update part 1 a little bit so that it's more amenable to having part 2 added to it. I added a function to OTP keys, which is the hash function to use. And then I pass our basic hash function into that. I forget, what was... Yeah, so we had a function called key, we renamed it to basic hash, and then we made it a parameter to the OTP keys function instead of hard-coding it to key. Okay, so this is kind of nice because it lets us... Splitting this into like multiple commits, I think, was kind of nice because it lets us like change part 1 and then separately add part 2. I don't know. Maybe it's just silly, but... Okay, implement the key stretching hash, and here's where I actually implement part 2. I define another function called stretch hash. It takes as an argument how many times to stretch it, and it defines a function inside of itself that it's going to return. Right, so we just return cycle here. So what that cycle does is it takes an n, which is the string that or the number that we want to hash, calls basic hash on it, and then cycles times it calls MD5 on the hash it's computing. So it does the key stretching part, right? And so I also defined a function named solve that has like the stuff that was in main before, so that I didn't have to duplicate it. And then I just call solve solve with basic hash, and then solve with stretch hash of 2016. And this runs a bit longer. It's like, I don't know, 30 seconds or something, maybe. So you can imagine that 1,000 times would be pretty bad. 30,000 seconds, I mean, you could maybe wait that long, but you certainly wouldn't want to. And notice we're still doing some extra work, right? Now that hashing stuff is so expensive, hashing 2 objects every cycle instead of 1 is like kind of, we could save some real time, if we could figure out how to not do that extra hashing. And certainly that's a thing that we could do, but it was fast enough, so I didn't. And it was kind of hard to figure out exactly how to like, do we cache the hash values? So one of the reasons that I didn't go with like this queue approach, yeah, I don't know how, like, a queue would be hard. I don't know. You could sort of keep, yeah, I don't know exactly what you would do. Certainly it is possible, right? I'm not claiming it is impossible, but it's kind of tricky, and we didn't. Doubling the size of the problem is not too bad. Multiplying it by 1,000, that's bad. But doubling is, like, fine. You know, the problem is running in a reasonable amount of time. Twice a reasonable amount of time is still pretty reasonable. So, of course, this gets us the right answer. I wonder, like, let's just try running it. So there's part 1, and I don't know, part 2 takes, in principle, 1,000 times as long as that. 2,000 times, really. I feel like it wasn't actually that long. It was a couple minutes, but I mean, it's not that exciting to just watch this run, right? So let's not. And we're still in the middle of this rebase, but actually that's a trick. We're not really, because the next few commits are the next puzzle, puzzle 15, which I have already finished, and we will get to in the next video. So if you guys are interested, stay tuned. Thanks for watching, and I'll see you next time.